Section 10 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 8, The Solar System, Part 2. For many years, the solar system remained in its fancied integrity. There was no change in the original 5 planets, and the number of satellites first discovered by Galileo and added to by subsequent observers had reached an apparent culmination when G.D. Cassini had detected the second pair of satellites of Saturn in 1684. Accordingly, when Herschel, following his custom of making a review of the heavens with each new telescope that he constructed, found March 13th, 1781, with a Newtonian telescope 7 feet in length, a small star which appeared so much larger than its companions and of such uncommon appearance, he suspected it to be a comet. Further study revealed that it was more than a comet and of far greater interest. When heedfully observed and its path calculated, it was found that no ordinary cometary orbit would in any way fit its motion. Anders Johann Lexell first recognized that Herschel's body was not a comet, but a new planet revolving around the Sun in a nearly circular path and at a distance about 19 times that of the Earth and nearly double that of Saturn. A vain attempt by Herschel to name the new planet after his royal patron George III, Georgium Sidus, finally resulted in the proposal and acceptance by British and continental astronomers alike of the name Uranus, which harmonized with the names of the other planets. This discovery was of especial interest, inasmuch as Johann Daniel Titius, a professor at Wittenberg, had pointed out the remarkable symmetry in the disposition of the planets. In a note published in 1772, he showed that the distance of the 6 known planets from the Sun could be represented with a close approach to accuracy by a certain series of numbers, increasing in the regular progression 0, 3, 6, 12, 24, 48, etc. Adding 4 to each number, the results would give the relative distances of the 6 known planets from the Sun. In applying this law, which does not hold good in the case of Neptune, it was found that the term of the series following that which corresponded with the orbit of Mars was not represented in the list of planets. Accordingly, Johann Elbert Bode, a German astronomer, assumed a hypothetical planet to take this place. When Uranus was discovered, its distance was found to fall but slightly short of perfect conformity with the law of Titius, and it stimulated the search for a new body, which, as will be seen in the chapter of the planetoids, proved to be the small planet Ceres. The study of Uranus, after its discovery by Herschel, furnished many discoveries to astronomers. Despite the most careful calculations of the movements of the planet through more than a century's observations, the conclusion was reached that considerable errors existed or that the planet was wandering from its course. In fact, these disturbances had aroused the interest of several mathematicians and astronomers, and a young English student, John Couch Adams, soon after his graduation from Cambridge, communicated in 1845 to the Astronomer Royal numerical estimates of the elements and orbits of the unknown planet, which he assumed was acting on Uranus and was the cause of the disturbances. In fact, he indicated the actual place in the heavens of the hypothetical planet. At practically the same time, a French astronomer, Urbain Le Verrier, who had made a careful study of the solar system in response to a request from Dominique F.J. Arago, the head of the French observatory, prepared an elaborate memoir in which he demonstrated that only an exterior body could produce the disturbances observed, and that such a body must occupy a certain and determinate position in the zodiac. He also assigned the orbit of the disturbing body, indicating that it would be as visible and bright as a star of the 8th magnitude. In fact, he supplied data to Professor Galle of the Berlin Observatory, which enabled that astronomer to find in the heavens on September 23, 1846, within less than a degree of the spot indicated, an object with a measurable disk. A reasonably complete map of this portion of the sky, in which all the stars were noted, proved beyond question that the object was not a star, while its movement, as predicted, was ample confirmation of its planetary nature. Adams' work, which antedated that of Leverrier, had not received attention originally in Great Britain at the hands of the Astronomer Royal, but as the matter assumed importance, the Cambridge Observatory also participated in the search, and on September 29, 1846, the planet was seen again. Thus, Neptune was discovered. To show the rapidity of astronomical research in the 19th century, it may be remarked that it required but 17 days for the discovery of a satellite by Lassell with a 2-foot reflecting telescope. Astronomers have suspected the existence of still other planets, and the belief has been expressed that such a body exists nearer to the Sun than Mercury, which, as has been seen, enjoys the reputation of being the closest of all the planets to the central luminary. The average distance of Mercury from the Sun is about 36 million miles, so that there would be enough space for such a planet. Its peculiar position in close proximity to the Sun, however, would act against its being observed. A small luminous point in this position would be altogether invisible, even with the best modern telescope, while its setting and rising, simultaneous almost with those of the Sun, make it invisible at these times, even under the most favorable conditions. If this planet should pass across the Sun's disk, just as do Mercury and Venus, it would be seen. While from its size it would be much less of a spectacle than the two planets mentioned, it might be detected. Claims have been advanced by astronomers that they have seen such a transit of a small spot. The first suggestion of an intramercurial planet came from the distinguished French astronomer Leverrier, who in 1859 advanced such a hypothesis in an attempt to explain the movements of the planet Mercury. His theory involved a body of about the size of Mercury revolving at somewhat less than half its mean distance from the Sun, or at a greater distance if of less mass, and vice versa, whose motion in great part would explain the irregularities observed. In the same year, Dr. Lescarbault at Orgères maintained that he had observed such a body crossing the Sun's disk, and the name of Vulcan was bestowed upon it. Several astronomers claimed to have seen the new planet. Their observations were not well authenticated, and on the dates fixed for the probable transits, no trace of the planet could be found. The strongest test was the examination of the sky at the time of a solar eclipse, for then the light of the Sun was cut off, and a strange body could be readily identified. Despite a careful watch at subsequent eclipses and an examination of photographic plates, only negative results have been obtained. Today, the belief that there is any body of considerable size within the orbit of Mercury is held only by a few astronomers and very guardedly stated. If the search for an intramercurial planet was unsuccessful, it has in no way deterred astronomers from endeavoring to find other unrecognized members of the solar system. Much interest has been aroused by a hypothetical ultra-Neptunian planet, which of course would be the furthest from the Sun of all the members of the solar system. The basis for such a hypothesis is the reduction of observations made of the positions and motions of Uranus and Neptune. Neptune has been under observation for only a small part of a revolution, so that data thus far obtained seem to many astronomers insufficient for the purpose. Yet a number of astronomers have sought by calculation to prove the existence of such a planet. While their results are discordant, yet they indicate very closely the regions of the sky where search for the hypothetical body might be rewarded with success. Professor W. H. Pickering of Harvard in 1909 evolved a method for the discovery of the distant planet, a method which he first tested by application of the data available to Adams and Leverrier for the discovery of Neptune, and found that the method would succeed. Proceeding then with his hypothetical planet, which he termed O, he found that it was 51.9 times as far distant from the Sun as the Earth, though its mass was but twice that of this planet, and that it had a period of revolution of 373.5 years. The problem presented by Uranus, Neptune, and O, according to Professor Pickering, is quite the same as that of Mercury, Venus, and the Earth, which has been thoroughly studied, so that the relative motions are well understood. But in investigating the effect that such a hypothetical planet would have on the motion of Uranus, Professor A. Gallo recently arrived at the conclusion that there were indications pointing to the possibility of still another and more distant planet also exercising a perturbing influence. The results of his calculations and studies therefore indicate the possible existence of two ultra-Neptunian planets, one at a distance from the Sun equal to 44 times the Earth's mean distance, and having a mass of about 1/64,000th the mass of the Sun, the other having a distance 66 times that of the Earth, and a mass of about 1/14,000th that of the Sun. While these figures disagree with those of Professor Pickering, yet the position calculated for the second planet agrees quite closely with that of the Harvard astronomer. The problem is by no means solved. It is mentioned to show that a plausible case has been made for at least one ultra-Neptunian planet. After astronomers had definitively decided how far the planets and the Sun are situated from the Earth and how they move with respect to one another, they began to wonder if perhaps the whole solar system did not in turn revolve around some central orb. The possibility first occurred to Tobias Mayer, Jean Michel, and Joseph Jérôme Lefrançois Lalande, but the problem was not attacked with any degree of success until William Herschel in 1782 began to draw conclusions from his study of the Milky Way, and decided that the entire solar system was drifting toward the constellation Hercules. But Herschel's theory did not meet with general acceptance for many years. Other astronomers suggested various stars as possible central suns controlling the movement of our solar system. Thus, Mädler not only proposed that Alcyone, the principal star in the Pleiades, should be the central sun because of its situation at a point of neutralization of opposing tendencies and consequently at rest, but even went so far beyond the limits of astronomy as to declare that, quote, "here was the seat of the Almighty, the mansion of the Eternal," end quote. It is hard even for science to quell the imagination and to confine an observer to facts. Mädler's theory was short-lived. Further study of the stars demonstrated the soundness of Herschel's views. When a modern telescope is turned toward the Milky Way, this white girdle of the celestial sphere is resolved into a vast number of stars, of which more than 140 million already have been counted on photographs. Each of these stars is a sun like that which governs the Earth, probably surrounded by planets like the Earth, and all these solar systems also are moving, many of them more swiftly than ours. It was inferred from Herschel's measurements of stellar positions, distances, and motions that the solar system was situated comparatively near the center of a universe shaped like a thin double convex lens. This universe was supposed to rotate as a unit about its center, with the result that the Sun, comparatively near that center but absolutely at an immense distance from it, moved in a circle of dimensions so vast that since the discovery of its motion, it had not deviated appreciably from a straight line, but had steadily directed its course toward the constellation Hercules. This simple scheme must now be abandoned, for it has been discovered by Professor J.C. Kapteyn, a Dutch astronomer, that the visible universe consists of two distant parts. The scientific imagination is compelled to picture two processions of stars moving in paths which make an angle of 115 degrees with each other. One of these stellar streams moves 3 times as fast as the other. The Sun forms a part of one of the streams and is at present at their intersection. Although it is known in a general way that the entire solar system is moving through space at the rate of 12 miles a second, the shape and size of the Sun's orbit are utterly unknown. The changes of environment, accordingly, that will accompany the description of it defy conjecture. The actual course of the solar system is inclined at a small angle to the plane of the Milky Way. Presumably, it will become deflected, but perhaps not sufficiently to keep the system clear of entanglement with the galactic star throngs. In the present ignorance of their composition, no forecast of the results can be attempted. They are uncertain and exorbitantly remote. Hence, in a sense, the world knows where it is and in what direction it is moving. But what is the goal? When shall it be reached? And what will happen then? Or, in this crossing of the congested thoroughfares of the heavens, will the world be shattered by a collision and resolved into a glowing nebula? This has been the fate of many stars, of several within the period of human history, and of one, Nova Persei, within a few years, and witnessed in all its destructive detail by astronomers still living. End of Section 10. Recorded by Dan Longauger in Washington State.